So, welcome to the NPTEL course on storage systems again. So, in the previous class we looked at some aspect relating to block devices. I will just mention one more type of block device. It is called the network block device. Okay. Now, instead of having your devices on a bus or what is called a storage area network protocols, right? You can use standard TCP/IP. Okay, that means that your devices are not connected through electrical or some special storage protocols. They are connected through regular TCP/IP, the internet protocol. Okay, or Ethernet networks. It could be Ethernet networks. It could be standard TCP/IP, whatever. Right. Then the basic idea is that you want to see if it is possible to collect various devices and make it look like a very big device. So, similar to what we talked about a volume manager last time, except now it is going to be through network. So, what is the previous situation? We had various disks, disk 1, disk 2, etc. And if you use RAID 0, we basically want to provide, if this is 4 terabytes, 4 terabytes, 4 terabytes, I want to provide a 12 terabyte disk, if this 4 terabyte each, right? And that we said is job of volume manager. And typically, in most of these cases, they are all sitting on a bus, okay, and it is all within a system. You are not using any, you are using some electrical protocols typically to connect each of these guys, to talk to each of these guys, to pick up things, put it right, read and write. Suppose I want to do it across the network, basically you still have the same thing, but you now go through some system, okay, and there is another disk that is going to another system, another subsystem. These guys are talking TCP/IP or Ethernet, okay. And basically the idea is to still give this is 4 terabytes, this 4 terabytes. Now can you provide a 8 terabyte disk, RAID 1, RAID 0, okay, but it is now through TCP/IP. That means you need to have two systems here. This system talks to this disk, system 1, system 2 talks to this disk, and so these two systems are also in picture. Previously it was being done in the controller itself. Okay, because it was done in the controller, it could be possibly more efficient because it is being done at a very lower level. Here the system has to come into picture, operating system is going to be in the picture, right? All kinds of things are going to be there, so the delays and latencies can be substantially higher here. But the good thing about this is that these systems can be disparate. This could be a Red Hat system, this could be a Solaris system, right? I mean, so a lot of things can change. This can be one type of disk, this can be another type of disk. For example, this can be SCSI disk, fiber channel disk. This can be a IDE drive, whatever. Okay, it could be solid state disk, whatever. Right? They don't have to be same, because finally the systems here are basically making them so that they all look same to TCP/IP. Okay, because finally only bytes are coming out. Right, does not matter which form, what it is stored in what form. Okay. So, the good thing about this is that you have more flexibility, but it can be slightly slower, and the other thing is here typically, since it is electrical protocols here or SAN protocols, you are limited to smaller distances, whereas here they can be on internet scale. It can be one thing can be sitting in Japan, another can be sitting in some place in India or US, wherever, like you do not care, okay. So, those kind of things are also possible, okay. So, you can use IP networks or Ethernet networks. Nowadays, Ethernet has become very popular because now we have what is called metro Ethernet. That means it is Ethernet across a city. So, you take a city of about 30 miles or 50 kilometers or whatever, right, in radius, you can use Ethernet as long as you use fiber, and you can design systems based using only Ethernet protocol, not even TCP/IP. Okay, that is, you are working strictly with Ethernet kind of protocols. Okay, typically you have TCP/IP layered on top of Ethernet. That means you have a higher level layers L3, L4, L5, etc. on top of L2 data link layer, right. Now you can have designs also which only use L2. Okay, and this Metro Ethernet and those kind of things have come recently in the last so many years, which has made this completely practical. Okay, so basically now you can get gigabit Ethernet across a city. Okay, so once you have gigabit Ethernet across a city, you can connect them. Okay, and now there are various vendors who will provide you. For example, you can say I want 300 megabits per second between 4 or 5 nodes in the city. Okay, and if you have such things, then you can build a network block device. You can. Okay, but the problem with this kind of device is that it has higher rates of failure. Okay, now the failure can be for two types. The data is intact, but your connection went off. Okay, or the data itself goes off. There are two possibilities. With networks, typically, data might be still there, but the connection is gone. Okay, you essentially have the non-availability situation. Okay, so now typically networks are much more fragile than if you use bus-based systems or SAN-based systems. Okay, on a PC, for example, once you put your disks, typically, unless you do a lot of shaking the PC or there's a lot of dust or such, or you pour water, things of that kind, usually nothing happens to it. Okay, it continuously runs without your doing anything with it, right. So the electrical connections are made properly and once for all. Okay, and usually once properly set up, usually they don't give any trouble, right. The disk might fail, but the connection may not give you trouble typically. Okay, whereas in the case of networks, all of us know the networks, they are a bit more chancy. Okay, and even more chancy if you use wireless protocols. They have phenomenal, amazing amounts of errors possible. Okay, so with networks you have higher rate of failure, so that means you have to really do something more serious about it. You can't take it easy. Usually you shouldn't take it easy even on a bus-based system, but here you have to be even more careful. So you need to have some redundancy in software. I think if you look at it, I mentioned it has to go through some systems, right, for network-based block devices. Now you should ensure that those systems are doing some redundancy, okay, in software. Okay, if they do it, then there's something okay. So I already mentioned these things are slower, but probably more flexible. The good thing about it is it allows for much higher scaling. You can now have worldwide systems, okay, because IP can go everywhere. SAN protocols, we will discuss it later, usually are limited to about wherever fiber can go, and there is some limitations on the round trip time. Okay, so because of the round trip times, for example, 30 miles round trip time is okay. On the speed of light, if you take into account, you are just about able to manage it. Okay, it takes if you calculate it, you will find that going beyond 30 miles or 40 miles creates problems for protocols like SAN protocols. Okay, so you can't really use some of these things, but with IP, it has been designed with a slightly different perspective. It's able to handle larger amounts of latency and longer distances. Okay, so that's why you will find that if you use IP kind of networks, then you can do a lot more scaling. Okay, even Ethernet networks may have a problem here, because Ethernet also you need to do some timeouts, etc. They usually set to be small values, whereas TCP/IP timeouts are slightly bigger to handle larger networks and worldwide networks. Okay, now so I'm not going to discuss this, but there is also an issue of parallelism, how to ensure that multiple activities, multiple actions, multiple accesses can be going on at the same time in this kind of network block devices, but I think I'll not discuss it right now. Okay. So what we have done so far is we looked at a simple character device driver, counting interrupts. We also looked at some aspects of the block device. I just briefly mentioned something about network block device. Okay. We will start looking at network based storage systems soon. I just wanted to say that is an important issue, and networks are critical for scaling. Only problem with networks is that the failures are very high. So, your error management or failure management has to be really very good. So, absolutely critical thing that you have to do. Okay. Okay. Without that, this whole thing just falls apart. So, if you look at all these Google file systems, etc., they are basically based on network based models. Their file system is based on having a network across many nodes, and together they provide the file system. Okay. That means that for them error management has to be central. Okay. The only reason why Google file system works is because of error management. Okay. They are able to handle it, and they have a system which is, I don't know how many nodes, they say, some people say 1 million servers are there or whatever, some people say 5 million servers, whatever. Okay. And they are actually have a lot of storage, and the storage is available anywhere, any place. Okay. And all is happening through networks. Again, the issue is what level at which you can do it. You can do it through a block device, or you can do it the file system. Block device means you are exposing at the level of at much lower levels, whereas the Google file system has decided to do it at a file system level. Okay. The reason why they have done it that way is because they use the native file system like ext3 on the nodes, on top of it they constructed it. Okay. So that we now have a simple file system like ext3 working reliably for them. They don't have to worry about a lot of things with ext3 handles. They only handle the upper layers, things for example redundancy across geographically dispersed areas, whatever. Okay. In a sense, what they have done is it's a division of labor. ext3 is doing what it's good at, handling files locally. Okay. Then you have the Google file system, a layer on top of ext3, which is good at doing things like working with large block sizes, 64 megabytes, working at replication, working on things like error management, failure management. What happens with that particular, I have 3 copies, 1 copy is gone. Should I keep 1 more copy? How do I sync it? Okay, with whatever 2 other copies that are there. Okay, all those issues are handled at the GFS level. ext3 is some kind of a lower level service which is used to construct a higher level service. Okay, that's what is going on. Okay, so all I just want to end this particular discussion by basically saying that there is higher rates of failure, and that is the reason why if you now multiple types of, let us say, failure management will be happening, ext3 will handle certain types of failures and Google file system will handle some other type of failures. Same thing with all these newer things called Hadoop file system, Cluster-FS. All these file systems also have 2 level structure. The lower level traditional, let me call it node based file systems, they will do certain things, and you put some additional things on top of it, so that it's across multiple nodes. You basically, so that you can scale on a much larger, at a much larger level. Okay. Now let's also try to look at some issues regarding devices and storage design. Okay. So we will look at, for example, the FAT file system. I think many of you are familiar with the FAT file system, and it's extremely simple file system. It was designed in the late 70s, okay, and early 80s, and it's widely used even now because it is the way your memory sticks, your camera, all these things actually use FAT. Okay, it's widely used. It's an extremely simple system. For example, a file is nothing more than a linked list of clusters. It's a very simple design. Okay. That means that if you want to get to one particular cluster, you have to walk over the list. It is order of n, depending on how much you have to walk. It's a very bad design, you might call it. Okay. It's a too simple a design. Okay. I shouldn't call it a bad design, it's too simple a design. Okay. So, so people want the more advanced file systems don't use linked list of clusters. They use, for example, B trees, or it could be some tree-like structure like Unix does. Okay. So with multiple levels of indirections, okay, various other things are possible, so that you don't have to walk through that order of n. Okay. You want to do log n typically, and but this being an extremely simple system, it uses linear link. And this may be quite appropriate. For example, you have a camera, right? Most of the time you are writing sequentially, right? And typically things are coming in large chunks. For example, you take photos for some 24 photos or 100 photos, and then probably you delete all of them. So in a sense, you have a huge sequential whole, which again you can use later. Okay. So camera is an example where linear linked list of cluster is perfectly fine. Okay. It may be also fine for memory sticks. Okay, because you basically what you're doing, how are you using memory sticks? They're basically using it to transfer files from here and there, right? And if you keep writing sequentially, probably it's perfectly fine. Okay, but for a regular high access file system shared by a lot of people, this will be not a good system. Okay. Now let's look at what this particular FAT file system, what was it for? Originally it was designed for floppy devices. Okay. The FAT file system came on floppy devices first, and it migrated to a disk later. Now it has migrated to SSD also. Okay, SSD, that is your memory sticks, cameras, obviously, right? So it has gone through multiple kinds of devices. Okay. Now the thing about a floppy device is that it is highly unreliable. Compared to a disk of those days also, a floppy was highly unreliable. It could bend, somebody can keep it in the sun, any number of things, right? So one way they decided to take care of error management was to have what is called 2 file allocation tables, 2 copies, okay? So that if one part of it became bad, you can read from another one. Of course, the bad thing about this is that anytime you update it, you have to update 2 places, so it becomes slow. But floppies by definition are not fast, so no problem. Okay? You don't care, okay? Because if some human beings are writing and reading, once in a while, of course, you can use floppy based systems even for doing computation, but that was only in the very early days. Most often, that's used only as an input-output mechanism. Okay. So now these FATs have also gone into flash, as we mentioned before. Okay. Now you can see that previously you had 2 FAT tables. The reason why the FAT tables was there for what? What reason? It was there so that if one part of it became bad, other part could be used. Okay. Basically, it's keeping track of the FAT table is keeping track of each file, which order it is, okay, the various clusters in which sequential order it is, right? And also it keeps track of which clusters are bad. Basically, cluster is a sequential set of sectors. Okay. So it's also the FAT is also keeping track of which areas are bad, okay, and which are unallocated. Okay, all those things it is doing. Okay, and if there is allocated files, the file will have a pointer, and you can go through the linked list of pointers to get the complete file. Okay, that's basically what FAT is doing. Okay, so the FAT is very important. So that's why there was duplication in the early floppy devices. But suppose I put on a flash. What is the issue about a flash? What about a flash? You have basically, if you really want to use flash properly, as we discussed earlier, you don't want to do update in place. To do update in place, essentially you have to erase the whole thing. If you want to write small thing here, if you do update in place, you have to erase it completely, a much bigger area. Okay, it's a pretty awful way of using flash. So because of that, you typically have no update in place. You write one place, if you have to you again want to rewrite on that same thing, you actually get a new erase block. Okay, you write there. Okay, and you continuously try to fill up that new erase block that you got. Right? And that means that by definition, you are moving around your FAT physically where they are going to be located. Previously, in the floppy case, your FAT is always in one single place, right? And if that got bad, you are in trouble. What about here now? You are actually smearing your FAT table across good parts of your device. Every time you write a FAT, that guy is going moving somewhere else. Okay, right? That means that you are not so concerned about error in one particular place. You have to worry about errors in general about the whole place rather than one particular place. See, what is the reason why you worry about disks and floppies? If you have a single dust particle somewhere, you might have completely that whole area is gone, right? And that might be a few blocks. Okay. Whereas with this system, even if there is some problem somewhere, you can always, anytime you write it, you move to some other place. Okay, so you are always doing it all the time. Okay, so every update to a logical cluster in FAT will be returned to a different physical cluster. Okay. Therefore, having another FAT may not be that critical. So, some people have decided that for flash you don't need a second copy of the FAT, throw it out, not necessary. Okay. So, that is one type of design, some people have started using it that way. The other possibility is, now given that I have freed up one FAT, can I use it in more interesting ways? One way to do it is what is called make it transactional. What is this transactional? I think as we discussed earlier, when you do a file system operation, you might update multiple things. Okay. Now, if you conclude the operation, all the changes should make it to disk or none of them should make it to disk. Okay. What I am not happy is part of it make it, part of it don't make it. A transactional file system will guarantee that any logically connected operations, updates, they will all either go to disk or not. Okay. Now, in the case of non-transactional FAT kind of file systems, you have this problem that if you take the floppy out while it is writing, etc., you are in trouble. Right? You are right. If some power fails as you are writing, there could be problems. Okay, if you are not updated, suppose it's not transactional. So the question is, how do we make it transactional? One way is there's a new type of FAT file system was designed. It's called transaction safe FAT file system for flash, because flash anyway you have one extra. Typically you have, instead of 2 FAT tables, now you have only one, other can be used. Okay, so it makes sense for flash. Okay, so this was designed for mobile kind of systems. Okay, not desktop systems, mobile kind of systems. Okay, and what do we do here? You basically change the design of this file system, a driver level modification to original FAT file system. So you still have two FATs, FAT0 and FAT1, but these are not going to be always synchronized. They always all have it. What do you do? First you make changes to FAT1. Okay, and only when you know that all the changes corresponding to an operation, file system operation, are complete, okay, then you try to update FAT0 from FAT1. So it's always the case that one place will always have a consistent version. Okay, see, it's not one is not saying that when you're updating from FAT0 that also can stop, but the thing is that FAT1 is now intact. Okay, so one place at least is always intact. Either FAT0 is intact because I was updating FAT1 and something happened, or I finished FAT1 and I'm trying to copy it to FAT0 and something bad happened in while I was updating FAT0, but I have FAT1 consistent. Okay, so you always have some kind of a consistent view of the file system. Okay, that's possible. Okay, so this has been designed. It turns out it has not been widely used because they are not available in desktop systems. So if you want, normally why do we use? We always go back and forth between mobile devices and desktop systems, right? Because all the serious work happens not on mobile devices typically, even now. So the thing is, there is still a problem. If it was available in desktop systems, probably it would be more widely used, but it's not available. Okay, these are some commercial things. This is Microsoft business. Okay, why they have done it on only for mobile, not for desktop systems. If it was on Linux, probably they would have made available everywhere. Okay, but this TFAT is a proprietary file system, so it's available only on mobiles, Windows mobile systems. Okay, so I just wanted to give you some indication that your design starts very much dependent on your storage design depends very much on the devices and various ways you can exploit the device. We will just look at it one more different type of this. There is something called flash friendly file system, okay, which recently has become part of Linux. This is done by Samsung, because Samsung is one of the biggest manufacturers of flash nowadays, and they designed something called flash friendly file system. Let us briefly look into what this is all about. Okay. First of all, you should know that this particular file system is not for raw flash. What does it mean? It assumes a file translation layer. We discussed this before. What is a file translation layer? Basically, Okay. What happens is that since there is no update in place is what you are looking for. So, if there is some block here, it's something, some pointer is pointed to this, and then you update this, okay. Then this pointer should be broken and it should point to this. So, there is some table out here which does this, okay, and this is needed for every update, okay, and somebody has to keep track of it, and that is done by translation, the FTL, okay. So, every single updates you have to keep doing it, okay. Now, this FTL, in addition to doing this, it also does things like what is called wear leveling and also what is called garbage collection. Both these things are done, okay. So, what is wear leveling? It tries to ensure that if this is the device, all of them are erased an equal number of times if possible, equally if possible, okay. So, at any point in time, the wear level number of times errors happened here or number of times errors happened here or here should about be same, approximately same, okay. That is wear level. What is garbage collection? As mentioned before, you are writing in, you have erased blocks, but writes are much smaller than that one. See, write could be this much, each write could be this much, but erased block is this much. So, it may be possible that I wrote this, I wrote this, I wrote this, but I overwrote this one. Because I am doing overwrite, actually this means that no longer the pointer is pointing to this, it is actually pointing to some other place. So, this value is dead now, this area is dead. Similarly, this also could be dead. We can also imagine that someday this also becomes dead, okay. Now, if this also becomes dead, you can see that most of it is dead material, only few are live, let us say these two are live. So, if I want to erase it, if I need some space, okay, ideal thing would be to copy this into some place, okay, into a new erase block again, okay, copy it here, copy this, okay, two places, okay, this guy goes here, and now this can be completely erased, okay. Once you erase it completely, now it is available again for allocation, okay, this is garbage collection. So, what is the problem with garbage collection? You have to first do the copy, which is can be significant cost. Second thing is, you are doing another extra write. You are reading it, but you are writing also to a new erase block. So, you are introducing extra writes, and there is a measure called write amplification, that happens due to garbage collection. If you do not do any garbage collection, that extra 2 writes will not happen, right, because you did garbage collection, 2 extra writes also happen. So, in a sense you can average over, given the so many writes you are doing, application writes, how many extra writes you are doing because of garbage collection, you take that ratio. So, people do not want a very high write amplification, it should be as close to 1.0 as possible. 1.0 is impossible, that means you are not doing, essentially you do not have any garbage collection going on. You want it to be 1.1, 1.2 somewhere in that region if possible. Okay. So, this particular system assumes there is an FTL. A raw flash will not have any of these things. The file system itself has to do all of these things. It includes, for example, remapping, it might include garbage collection, wear leveling, all those things have to be done by the file system if the file system is running on top of raw flash. Whereas, if your file system is running on top of FTL, then the wear leveling, garbage collection, all those or some of the remappings etc. is done by the device itself, the FTL enabled device. Okay, that most of the things we carry around, memory sticks, they all have FTL inside them. Okay. So, most widely available stuff is FTL based. So, if you design something for raw flash, most likely there is not enough market for it, because what people want is somewhat simpler interface, and that is what FTL based storage devices do. Now, this particular system is based, there are some other file systems in Linux called JFFS2 log-fs for raw flash. So those things directly work on raw flash. Okay. We will not be discussing it here right now. Now this particular Samsung designed flash friendly file system is based on a log structure file system. Now let's just quickly look at what log structure file systems are. So the basic idea about a log structured file system is that you think of your device in terms of so many segments, okay, some hundreds of segments. I'm putting only 4 of them here. Segment 0, 1, 2, 3, and basically in memory you keep a memory segment. This is a disk segment or a device segment. This will be a memory segment. This will be, let's call it device segment. Okay. So what you do is, anytime any writes happen, you keep on appending the writes in the memory, keep on collecting them. You keep collecting, and basically what you do is, you also keep track of which block you wrote. Essentially this will be, you will create a structure by which you will know what block it is and the data corresponding to it. Okay. In some sense there is some more table somewhere saying that this particular thing is block number 5, this is block number 37 or 13, etc. But you are writing it contiguously. Okay. So this will be block number 5, 13, etc. But they are logically, they are not contiguous, but physically they are contiguous. Okay. So once you collect one complete segment worth of it, you can write it to the device. But while connecting it, you may find that this becomes dead. Okay, that becomes dead. You decide. You will see that is it worth cleaning it. If it is worth cleaning, I will clean it, and then once it is again semi full, I will put it here. Okay. So the idea is that you do it in memory first. You keep on accumulating stuff in memory. Okay. The only thing that you have to worry also is now that writes can always be, they will have the most recent value, right. For reads, what you have to do is, you have to, when you want to read, right, you have to read from the backward direction to get the most recent value. Okay. Writes are always going in this direction. Okay. But suppose suddenly I want to, because for writes I do not have to figure out where things are, I just have to keep on appending it. But for reads, I need to know where they are, right, because previously it was somewhere here, right, in some other segment. Because overwrite happened, I, instead of updating in place, I put it here. It could be in the same segment or some other segment. That means I need to keep a indexing table which tells me if I want to read something, where is the most recent copy. That itself again will be in memory. That indexing table also in memory, right. This is going to be updated every time any rewrite happens. Okay. So when you want to read, you have to look up this guy and see which is the most recent version of that one and look it up. Okay. So all of this stuff is in memory, and so you have to flush these things to disk every so often. Even this might have to be flushed to disk once in a while. Okay. Because this keeps the track of the read. If I want to read something, it has to be where the most recent copy is. Okay. So roughly what we are doing is, we are accumulating stuff, writing in big chunks, and then we also keep a indexing structure, so that for any block we want to know which is the most recent copy, where is the most recent location. Okay. All this stuff is typical in memory, but some of the structures for checkpointing purposes you might have to put it onto disk also, or into stable storage, or onto flash. So you have this is roughly the design of a log structured file system. Basically the idea here is the log itself, because what is a log? The way you continuously write, that's a log. The log itself is a file system that has everything in it. Okay. Whereas in other file systems like your ext3, ext2, etc., right, you always do update in place. Okay. So the log is actually not, if you use a log in those kind of systems, that is quite different from the actual data that is there. Here the log itself has everything. Okay. So it's based on log structured model. What we do is a segment is here 512 blocks of 4 kilobytes, about 2 megabytes. Okay. So your segments are 2 megabytes. That means you have to allocate 2 megabyte chunks of memory, and everything is accumulated there, and every so often approximately 2 megabytes will be flushed to disk. Okay, if you want. Okay. And then in addition they have to make it for even writing longer sections, many segments can be made into what is called a section. Okay. And typically it is in the 2 to the power of k, that is you either have one segment as one section or 2 segments as one section, 4 segments as one section. As I mentioned already, it is copy and write, data always written to a previous line space, read from the most recently written region, and mapping for reads changes for every update. Okay. That is basically log structure file system. And free space is managed in large regions that are written sequentially. Okay. So basically you manage in terms of regions, and these are written sequentially. And in terms of D1 for flash, just like for disk, writing it sequentially is better than writing it randomly. Okay. So what do we do? Again, as I mentioned before, you have to do cleaning. When number of free regions becomes low, your live data is coalesced from several regions into fewer regions and releasing the rest of it. Okay. So overhead is of copying is one of the significant costs of log structure. If you use log structure, the copying cost becomes important. In the flash case, the write amplification also is an important cost. These two things are important. Okay. So this particular system, they have also tweaked it quite a bit. So there most devices come from various flash devices. You have enterprise flash, you have consumer grade flash, you have camera type flash, you have MMCs. For camera you do some different things. There are so many different types of flash. Okay. So because of different characteristics, they have various ways to configure it. Okay. Also for selecting which type of allocation and cleaning algorithms to use. Now let's look at the interaction between FTL and LFS. It turns out FTL itself uses a log structure design. So now we have a flash friendly file system using LFS, and we have the FTL. Typically, if you see the design of the FTL itself, what is FTL? This is the translation layer. Okay. It turns out the flash translation layer itself uses a log structure design, because it is used to provide where leveling and write gathering, because that guy also has to write in larger chunks at the lower level, even if there is no file system on it. So that guy also using a log structured file system. So essentially this is an interesting design where there are 2 log structures active on the device, one at the FTL level, one at the file system level. Okay. But the way these guys have done the design, the top level F2FS, that is file system, it tries to exploit the characteristics of FTL. How does it do it? It knows that FTL is doing the business of where leveling. It is trying to distribute everywhere. So he doesn't try to bother about it. It says he is going to take care of it, I am not going to do it. So this business of where leveling is going to be best provided FTL, I am not going to touch it. But what I will do is, I will ensure that large scale write gathering happens, okay, in large sections. Okay. So, and FTL is much better at handling that, in send large sections. Okay. But actually even more specifically, instead of just doing it as a single large write, it keeps essentially, I am told, about 6 sections are gathering the blocks at the same time, 6 independent ones. Okay. What is the idea? It turns out that in any realistic system, various blocks will have different life expectancies. Some files are mostly stable, nothing happens to them. For example, /etc password, it changes only every time a new user comes in and goes. Whereas your cache, for example, if you are a Firefox, there is a cache directory and lots of files are written and lots of files are deleted. Okay, that's creation and deletion. And there are some other situations where a lot of updates take place. For example, somebody is keeping track of how many users came to your website. There is some small file which keeps in there, and it keeps on changing every so often, right? If it's a very heavily busily visited website, it will be changing every second possibly, right? So there are different files and correspondingly different blocks with different life expectancies. If I want to do some intelligent garbage collection, what is the right thing? I have to ensure that those blocks which have similar life expectancies are grouped appropriately. So for example, those things that don't change, if they are all in one place, I can clean them once every, let us say, hour, because they don't change much, and I just once in a while they change, and if I do it as slow as infrequently as 1 hour, it's okay. Whereas if something is happening very fast all the time, right, that means that many things are written and they get overwritten. That means that in a non-update in place kind of system, that thing already is dead. The physically that place is already dead. So if a lot of activity is going on and I group all the highly updated things in one place, even if I wait for a small amount of time, I just wait for 1 second, probably almost everything is dead, okay. And once in a while there will be a few things might be alive, I just copy exactly 1 or 2 things, right. So what the LFS does is to do this intelligent business of grouping those blocks that are changing according to their life expectancies, okay. That's what it is doing, okay. So that's one part of the thing, okay. In addition, as I mentioned, LFS, basically this flash friendly file system uses log structure file system, but doesn't use it everywhere. Why does it use everywhere? Because sometimes it has to update metadata. Metadata is typically small, it's information about a file. They may not be as big as the file itself. For example, you have a music file which is sitting on your memory stick. The metadata will be only probably at the most 512 bytes, sometimes even less, okay. It just tells you the author, let's say information about how big it is, when was it created, all those kind of things. That usually fits in 128 bytes or 256 bytes or 512 bytes, okay. So you're not talking in terms of 2 megabytes of segments or even longer sections or 4 megabyte section or 64 megabyte section. We're not talking about that. We're talking about smaller things. But the thing is, for correctness, you might have to update this metadata quite quickly, okay. So what they've decided is, the lower level is typically doing log structure file system, that is the FTL. Upper layer does it most of the times it does log structure, but when it comes to small updates, it says I don't need to do this keeping all these things around and then putting it into some big structure. It will take a long time, because if you take a 2 megabyte section, right, if you are only putting in small inode information, okay, it might take a long time before you are done with it, right. So it creates some problems. Basically what they do is, they say anyway FTL is doing this business of collecting things together physically, right, at the physical level, okay. I will do small transactions in place, okay. So it sounds so that by doing it, it simplifies the design, so they do that. So in a sense, it is slightly optimized for metadata, that part of it, the ones which don't go through the log structure file system part. So as I mentioned earlier, this F2FS has 6 sections open for writing at any time, different types of data written to each section. Different sections allows for file content to be separate from indexing information, okay, inode kind of things, and basically divides the data into hot, warm and cold sections, and this is done through some heuristics. Again, this is a part of the file system heuristics, okay. Again, it is not done best by FTL, because FTL doesn't know exactly the application level information. It has been designed by some vendor somewhere and it has no serious understanding of what upper level guys are doing, okay. Similarly, for example, directory data is treated as hot and kept separate from file data, okay. and because they have different licensing. Reason is that, for example, oftentimes you might keep some information about, see, in a particular directory there might be a lot of files, and anytime any file is added or deleted, you have to change the directory contents. And directories are luckily not too many in number, so they are changing up every time there is a file activity, and since they are smaller number, you can essentially keep them cached. That is why there is oftentimes something called directory name lookup cache, for example, in Linux. And typically these things have a different life expectancies. So basically you keep one of these sections as directories. Okay. So basically hot nodes expected to be updated soon. If you wait a small amount of time, a section of full hot nodes will have very few live blocks, cheap to clean, as already discussed before. Okay. The one big problem with this kind of systems is that whenever a block is written, suppose I have some tree like information. Whenever a block is written, its physical address changes. Because the physical address has changed, its parent in the indexing tree also must change, because finally you have a parent, right? See what is happening? Let us say that I have some information like this. If I update this, what will happen? The physical, because now we have no update in place. That means the address of this guy is no longer what this guy has already previously stored. That means this guy also has to change. Because this guy has changed, this also will be not update in place. That means this guy also will change. That means this guy also has to change. It goes all the way to the root. Okay. So one change here means you have to change everybody up, okay, which is a big problem. Okay. So basically, so there is a big problem with respect to this. So what people do is we have a special table for indirect into actual blocks. So what you do is you keep another special table, and that will always point to the correct new location. Originally it was here, it goes here, but the tree itself will store the offset into this. Okay. What you do is the offset is always fixed. So the tree is always changing, talking about offset into this table, this new table, but essentially you are indirecting it through a fixed offset location, and then that gets updated, but the tree itself is having the same offset all the time. Okay. You use a special table for indirecting to actual blocks. Tree actually stores offset into table only, okay, and that is fixed irrespective of all the changes you are doing, in respect of the, because you have this non-update in place, it will be going to various places, but offset remains fixed and the offset location will keep changing. Okay. So essentially they indirect at the same offset in the table, but our problem now is that the table itself is changing now. Okay. Now it turns out that they use a special technique called two location journaling to reduce overhead. It is similar to what we, when you talked about two special location journaling, it is similar to what we discussed in the case of this FAT0 FAT1. Remember the FAT0 FAT1, you keep one thing consistent and write to the archive, then you go back and forth, right. It turns out that they do something similar here. Okay. You have two locations for this node table, this is what they call the special table, and then they keep going back and forth. Okay. So that reduces some overhead. Okay. So basic problem is that every time you update, you have to start looking up another table. Okay. So they avoid it by some kind of recursion is there. So you want to avoid it by saying that I use this two location journaling like FAT0 FAT1 kind of model. That will essentially reduce the amount of additional tables I have to keep. Okay. Now let us look at one more thing as okay. Now it turns out that you keep many sections to do what's called as one. So basically now we have blocks, segments, sections and zones. Okay. Now zone concept has been come up. Basically the idea is that a flash device often made of number of fairly separate sub devices. Basically as I mentioned, if you look at a large SSD, it is made of many chips, and many chips for example, 9 of them it make into a bank, then you might have 64 banks, okay, some multiple interfaces, etc., right? And basically what will happen is that each of those sub-devices, right, if they can be accessed in parallel, okay, then you have parallelism, okay. So basically flash devices made up from fairly separate sub-devices, each of which can process other requests in parallel, okay. I think you are familiar with this part, okay. So if the zones, if you have some kind of a zones, which is a higher level structure, basically multiple sections making into one zone. If zones are mapped to sub-devices, then essentially 6 open sections can all handle writes in parallel and make best use of device bandwidth or minimize latency, okay. So essentially you are pumping the same device, 6 operations can be going on at the same time, because they are sitting on 6 separate groups of chips, and each group can be considered to be some kind of interface, okay. So each group of them is an interface, so I can essentially keep doing 6 or 4 or whatever it is, okay. That's even it says up to 6, depends on the device, okay. So it turns out the zones are basically the main area of the file system. There is also a meta area which contains metadata. As I mentioned earlier, these ones use much smaller sized units of information, inode kind of things, and again, instead of doing it in the flash file system to manage this thing, it is left to the FTL to handle it, okay. Now if you look at the inode structure, also there is some interesting things here also. Normally most people will say, why don't we use B trees, etc., or extents, okay. I think you are familiar with B trees. The good thing about B tree is that you give typically a log n kind of access path to get to any particular location, okay. Or you can use what you call extents. Extents are basically, instead of always storing in blocks of 4 kilobyte, you might store in terms of contiguous chunks. It can be 512 kilobyte chunk, it could be 4 megabyte, it could be 288 kilobyte, whatever it is, depending on the contiguous thing. You say that my file is composed of so many extents of contiguous nature, okay. So you might have a file with 288 kilobyte chunk followed with another 512 kilobyte chunk followed by 4 megabyte contiguous chunk. 3 extents, one of 288 kilobyte, one of 512, one of 2 megabyte, things of that kind, right. So surprisingly, this particular design uses only the standard Unix like inode. It has got this direct blocks, indirect blocks, and indirects also double and triple indirect blocks. Just like I think we discussed it earlier, right. It does not use B trees or extents, and there is a reason for it. We will come to that soon. It turns out the inode size is 4 kilobytes. It is much bigger than ext3. ext3 typically the inodes are 256 bytes or 512 bytes. This is much bigger because it turns out it uses what is called copy and write. For copy and write, it turns out using 4 kilobyte chunks is more appropriate because it's closer to the page size, and it turns out that that's better, okay. So the good thing about this is that if you use this kind of model, index tree for a given file has a fixed unknown size. Why is that? Because I am trying to clean stuff, okay. When I am cleaning stuff, it may turn out that I might get different, for example, let us say I have a ext extent based file system, extent based model. When I am just about, say the reason I am doing cleaning is because I want to get more space. It is using certain types of extents, but while cleaning, what can happen is that you might get different types of extents, because it is a concurrent system. While you are doing it, somebody else can run away with what is available, and it might be turning out that you are forced to use extents which are not as big as the previous one, because you are copying things around. So what is contiguous? What are the contiguous sets of blocks you get at the time when you are doing the cleaning? What is available for you to put your live data? That might be quite different from what you had, okay. So basically what will happen is that your size of your indirection can keep changing depending on the availability of extents at the time you are doing cleaning, okay. Now that is slightly a non-intuitive thing, because you are doing cleaning to think that you are getting extra space, but as you're doing it, it turned out you actually started to become bigger. It can happen. Okay. So this is not a nice thing. Therefore, if you use something like the standard Unix kind of inodes, it is a slightly more non-surprising in terms of its operation. Okay, it doesn't give you shocks. Okay, that kind of thing. Okay. So I think I just want to conclude here. I just want to say that if you think about the device, you will see that a lot of things had to be taken into account. The device characteristics has a lot of implications on the way the design of the higher level subsystems have to be. I just took FAT and the flash friendly file system as examples about how the non-update in place, right, how they have affected the design of the systems. Okay. So I think I will conclude here at this point.